Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and today I want to talk a little bit about clean code, because I was looking back at some of our older scripts from previous videos, and I was realizing that they are rather difficult to understand and to read. And in particular, since we want to be able to ideally reuse a lot of our stuff, we want to start trying to write our code in a much more reasonable way. And so that's kind of the focus of this episode. So I have an empty file here called Minmus Lander, because we've not sent anything out that has landed on one of the moons and come back, and we are just shy of enough science to unlock the larger engines. And I really don't want to invest a bunch of time into creating launch vehicles if we're just going to replace them with stuff using the larger engines as soon as we unlock them. So I want us to actually set up a script that will take a rocket, it will go land on Minmus, get some science, and come back. But I want to do this in an intelligent way, and so I want to talk about kind of the clean code approach to doing things. So we're going to start off by writing a function called main. Now, I'm not a huge fan of this main as a name. It's a convention used in a lot of different programming languages that this is the entry point for whatever it is that you're doing. So we're going to go ahead and adopt it here. Generally, I like functions that are a bit more descriptive about what it is that they're actually doing. You know, even if it was something like initialize or something, I don't know. Generally, verbs tend to be better function names, but this is something that goes back to very old historic programming roots. And I'm going to go ahead and just start writing what is the main point of our script, right? Well, so we would want to perform an ascent. Obviously, we'd want to perform a circularization. And let's see. So that'll get us, once we've done that, we're in orbit. Then we would want to transfer to Minmus, right? So we want to do that. Now, once we've transferred to Minmus, what do we want to do? Well, we want to deorbit. Let's see. Let's just say perform descent. We don't need to overthink, even if these things may include a couple of different steps. Like we may have staging in here as part of our ascent. We may have staging as part of our circularization. We may have multiple steps that are part of our transfer. We may have, first getting our inclination change and then doing a transfer, depending on how we choose to implement it. But we don't need to worry about that right now. We're just writing our main function, assuming that everything else is handled for us. So we'll perform a descent, and then we would have a function called gather science. And okay, so that gets us out of the atmosphere, off of the launch pad, out, ascended, circularized, transferred to Minmus, descended, gathered the science. Now we need to get back, so we're going to go perform ascent again. And yeah, let's go ahead and perform circularization just to be safe. And transfer to Kerbal. And let's see, then what do we want to do? Well, I think we probably don't want to do the same thing as perform descent, because we're going to do a powered descent. We're going down to Minmus. That's probably a little bit iffy for Kerbal. We may not have enough fuel at that point, depending on what our craft is. So let's see, perform parachute descent. Let's just call it unpowered descent. Right? And up here, when we say perform descent, we'll say perform powered descent. So an unpowered descent would be something where we're relying on parachutes to get us down. A powered descent would be something where we're relying on our rocket to get us down. So there we go. We have now written our entire program to get us to Minmus. Of course, none of these things actually exist, though. So that's a bit of a problem. But we can now say, all right, if I'm trying to figure out what is the point of this program, if we imagine that we're looking back at this in the future, we can go, okay, I have a very good sense of what this program is intending to do. And we could even break this up. We could have just a line space here, because, just to kind of look at these being various steps. But we can look and we can read and figure out, all right, I know exactly what this program is trying to do, and I know, generally speaking, I don't know the details of any of these steps, but I know exactly what all of this means. Now, The next thing that we have to do, of course, I'm actually going to go ahead and just delete these to make things easier, is none of these functions exist. So I'm going to go ahead and paste them down here, and let's see. I'm just going to go ahead and say function, and let's see, I'm going to go ahead and replace this with, let's see, space, this, return, okay, whoops. Yeah, okay, so it replaced all of them except the ones that actually have these parentheses around here, but that's fine. So we've got, actually, no, let me go ahead and do that again, except I'm going to put a to-do in here. To-do. I wonder if that's going to work. Nope, it's mad about. Let's see, I think I have to escape these. Yes, there we go. Okay, so all I did is I copied these names and then I just did some replacing to give us the actual functions. And except I don't like there's not a space after there, so I'm going to go ahead and replace to do with space to do. There we go. Okay, and of course this one didn't work because they didn't match that pattern. So we'll go ahead and put this in here as well. Now we've got some duplicates though. Transfer to we already have, though we want to make sure that transfer to actually needs to accept a parameter, body. That's the whole reason that it didn't work in the first place. We've got a couple of these that are duplicates. Let's see, perform ascent, we already have that. Perform circularization, we already have that. Let's see, gather science, transfer to, perform ascent, perform circularization, power descent. All right, good. Yes, now we have all of these things. And crucially also is that these are all in the same order. So if we're looking for perform ascent, well, that's the first function that's right after our main function. If we're looking for perform circularization, that's right down there too. All of these things are nice and easy to find. The last thing that we'd have is at the end of our program, we'd actually call that function main. Now, it's also important that because we're doing it this way, that we don't try and call anything outside of the function. If we tried to say perform ascent here, whoops, we might run into issues because we have not actually defined perform ascent yet. That's one of the benefits of putting the entire kind of runtime of your program inside a function called main, is that way you can make sure that you can define all of these other functions first, and then you run main, and by that point, everything is already defined. So let's think about these steps. We don't have to, our main function is done. We shouldn't have to touch this. We shouldn't have to change anything from here on out. This thing is completely finished. All we have to do is fill out these numerous functions. Now, if we think about perform ascent, we spent the last few videos talking about figuring out an optimal ascent profile, so I'm going to assume we're going to be able to do that pretty easily. We'll skip over that for now. Perform circularization, that's probably really easy too. In fact, we can probably even just prototype that here. We could say wait until ETA apoapsis is less than 20, lock throttle, well, lock steering, whoops, to prograde, lock throttle to 1, wait until orbit eccentricity is less than 0.1, maybe, and then lock throttle to 0, right? So this is not a great implementation, and we'll probably go through and clean this up, but we're just trying to go through step by step and say, all right, here are the things that we need to actually worry about, and we can replace these small little functions with better implementations without having to worry about, all right, is that going to affect anything elsewhere? All of the code inside here is completely isolated from everything else, so if we make any changes, we can do that without worrying about anything like that. And in fact, this is probably a really bad idea, because if we're just trying to make sure that we want our orbit to be circular, we may want to change this margin. We may discover that, okay, actually what we're doing is we're making our orbit less circular, that we've somehow managed to shoot past things and stuff has gotten bad. So we'll probably want to change that, but we can leave that there for now. Transfer to, now that's something that we have done, and for the most part we've done by just setting up maneuver nodes manually and saying, do that maneuver node. So we'll want to go ahead and work on that as well. But I want to look at performed powered descent, because this one is something that we've tried in the past. We've done some suicide burn stuff in the past, but it's never been particularly great. And so I want to try and see if we can figure out a better way to do that. So let's create a new file and start playing with the test script to get our suicide burn down. So this is going to be a separate program that we're going to use to test out our suicide burn, and we're just using this to get ourselves a prototype that we can eventually inject back into our Minmus lander. So I'm going to start out the same way with the function main, and let's see, well, how are we going to actually test our suicide burn? We're on the launch pad, presumably, so we'll have to say, let's see, initialize test conditions, and then perform suicide burn, right? That's all that we're trying to do. Though one thing that I probably think that we should test is that we ideally want to make sure that we're not using, we want to be able to figure out how much fuel we had to actually use to kill our velocity. So let's say local fuel is stage liquid fuel, and let's say print fuel used plus stage liquid fuel minus fuel. So this is just going to get the amount of fuel that was used in the process of doing our suicide burn. So there we go, we've got that. Let's go ahead and write a function for, function for initialize test conditions. And if we think about this, all right, so no parameters, we don't need to worry about that. Let's go ahead and say lock steering to heading 9090. Actually, you know what, let's set it to 270. And let's set the direction to 60. We're not going to go vertically because we actually want to be able to test that even if we're not coming down vertically, we're able to handle stuff. So let's go lock throttle to 1 and stage, and then wait some arbitrary number of seconds. Let's make it 10 seconds. And then lock throttle to 0. And let's see, so we're trying just to get ourselves to a position where it's appropriate for us to perform the suicide burn. And I think to do that, we'll go ahead and wait until ship vertical speed is less than 0. So we don't want to call our perform suicide burn function until we're actually, falling back toward Kerbal. Now, one of the good tips for designing stuff is that when we're doing, if your function is more than a few lines, it probably means that you're doing multiple things in a function, and ideally you would want things to be much smaller. So I'm going to go ahead and group some of this stuff. Let's say we can take this out. I'm just going to throw that down here, and we can take, let's see, this out. I'm going to throw that down here. And in fact, we can take this out too. I'm going to throw that down here. We're not going to have that in our function. Instead, we're going to call a couple of different functions. We're going to say perform launch, and actually, yeah, that's going to, you know what, since this is just one line, we can go ahead and put that back in. Perform launch, and then await conditions. Right, well, actually, let me think. These kind of go, yeah, we can think about just kind of how these are logically grouped. Waiting 10 seconds and locking the throttle. Locking the throttle is not part of awaiting conditions. Let's go ahead and write function perform launch real quick. There we go, oops. And we'll paste this stuff in here. Perform launch. And we've got await conditions. So let's see, wait 10 seconds. Technically this is part of our perform, well, we'll just paste that in here for now. We'll leave that in there and we can go back and tidy it up if we want to be really finicky. Await conditions. And we'll paste that into here. Now, This seems kind of dumb because we have a function that is just taking out one line of code, but instead, await test conditions. Name that. A little more helpful. So one of the reasons that this is actually helpful is now that we're looking here, we can say initialize test conditions. What does this actually do? If we're trying to just reason about this particular function, we go, okay, so it's going to perform some sort of launch. It's going to wait 10 seconds. It's going to throttle down, and then it's going to await some test conditions. We don't need to know what those test conditions are. We don't need to know that, it could be that we're waiting until we're out of fuel, or it could be that we're waiting until we've traveled some arbitrary distance. It doesn't particularly matter. And so the goal with writing a bunch of small functions is that at any step of abstraction, we should be able to get a sense of what a function does without being bogged down with the details. So if we're only trying to figure out what does this program actually do, we look at the main and we go, okay, so it's going to initialize some test conditions. It's going to get the current fuel, and it's going to perform a suicide burn and then print out the fuel used. Okay, cool. And then we go, okay, well, but what does initialize test conditions actually mean? Well, then we can hop down to here and we can go, okay, so this is what it's going to do. It's going to perform a launch, whatever that means. It's going to wait 10 seconds. And basically, we can just decide at some arbitrary point, all right, here's the point where I'm going to go, all right, I know roughly what this is doing. I'm just going to assume the perform launch is, going to do roughly what it says it does. And we can decide kind of how granular we want to drill down into these functions to figure out what's actually going on. So yeah, I think we'll go ahead and leave these. I'll put that on one line just to make it a little cleaner. So there we go, we've got that. Now let's write our function perform suicide burn. Nope, there. So what is our suicide burn actually going to be? Now the idea with the suicide burn is that we are moving down and we don't want to crash when we're going to move down. So let's go ahead and say until ship state equals landed, and we're going to have some sort of wait in there at the bottom. And what we want to do here is we want to control our throttle based on whether or not it needs to be throttling. And we're not even going to worry about setting our throttle to a particular value. We're just going to turn the rocket on or off depending on whether we think we're going to crash. So let's go ahead and say if velocity at impact is greater than 2. Then we'll say lock throttle to 1. Otherwise, lock throttle to 0. And of course, we can tidy this up a little bit. We can say that and get rid of this. And there we go. So this is a little bit longer of a function, but that's fine. We're looking at this. Okay, until we've landed, if our velocity at impact, and this is going to be a function, is greater than 2, lock the throttle to 1. Now there's a problem here though. And this bugs me, so I'm actually going to put this back in. And that is this value 2 here. Because what does 2 actually mean? It doesn't mean anything at all. We don't know what that is. If we're just trying to look at this function and not care about where it's called, not care about what this velocity at impact is, this value 2 is just a little bit iffy. So what I'm actually going to do is I'm going to go ahead and say maximum impact velocity. Now, of course, that means that we've actually got to throw a maximum impact velocity up here. So I'm going to go ahead and say set maximum impact velocity to 2. Now I am using all caps here, and this is because this is going to be a constant value. We're never going to change it. It's just configuration for how our script actually runs. And now when we're looking at this, it becomes a little bit more readable. We're saying, okay, if the velocity at impact is greater than the maximum impact velocity, we don't know or care that that value is 2. We're just trying to understand this function in isolation. We go, okay, so this is what happens if that's the case. Otherwise, we're locking the throttle to 0. So now we need our velocity at impact function. See, we're just going through and building these things up kind of from the top down, and we're throwing in these functions as though they exist and discovering, okay, now we need to write something. So velocity at impact. Now, how do we figure that out? Well, we know that velocity is equal to the initial velocity plus acceleration times time, or times time. So we can take that same optimistic approach. Let's go ahead and just say return v0 plus a times t. Oops, t, not 5. All right, there we go. Of course, we actually now have to set these values. We're optimistically coding in the assumption that we'll be able to set these to things. So I'm going to go ahead and actually do that. Now I'm going to say local v0 is, let's see, ship vertical speed, except the negative value of that because we're falling. And then I'm going to add, let's see, the absolute value of ship surface speed, or ground speed. That's our lateral velocity, because presumably that's something that we'll need to cancel out as well. So we set that, and now we need to figure out our acceleration. Now acceleration is a little bit more tricky because we need to figure out what our velocity is going to be based on both gravity and our acceleration from firing the rocket. We want to determine, okay, if we were going to burn at full speed, what would the situation be? So I'm going to go ahead and write in here local A is something. Well, it's going to be the acceleration due to gravity minus the acceleration due to thrust. Right? Now we're implying, okay, there's some more stuff going on here. We need a local A grav, and we need a local A thrust, and we're going to have to assign those to something. Gravity, we can figure out pretty easily. So I've gone ahead and just pasted that in. It's just the body mu divided by the ship altitude plus body radius squared, because we've got inverse square law stuff going on. The acceleration due to thrust is, let's see, the ship full thrust, or max thrust, divided by the ship's mass. And there we go. Now we've got A. Now the last thing we need is T, though. And to do that, well, we need to know when is our time to impact. So, okay, we're getting optimistic. We've already put in a T there, so let's go ahead and just say local T is time to impact. Right, we're just going to write that function. Now, we're not going to worry about this just yet. First, I want to look in here and say this function is getting kind of long, and it probably means that we're doing a bunch of different things. And in particular, these 3 lines are a thing that we probably shouldn't be doing in the function. Ideally, you want your function just to be doing one thing. That way, if it breaks, you know exactly what function broke. So what is this actually calculating? This is calculating, let's see, it's calculating acceleration at full thrust. Well, let's see, cumulative acceleration, maybe? I don't know, that seems as good a name as any. Let's go ahead and just put that back in here. Local A is cumulative acceleration. Let's not cumulative. Let's just call it total acceleration. All right, so we've got that, except we don't need to set a local here. We just need to return that. So we're going to return acceleration due to gravity minus acceleration due to thrust. And now this function is looking a lot cleaner to me. I'm much more happy with this. Actually, I'm just going to swap these out because these are not interdependent. I'm just going to make them match the same order as this function here. This is looking cleaner. We're just getting the starting velocity. We could even break this out into its own function, but yeah, we don't have to. We're going to set our acceleration to total acceleration, which we've put in our own function. We've set our time to impact. Now, this does mean that we've got 3 separate, two separate functions that we have to write, but it does mean that when we're just looking at the velocity at impact, we can understand what this is doing. So we're just returning the final velocity over the total amount of time. So we've written our total acceleration. Now we need to write our time to impact. And this is a little bit trickier, but we're actually going to use the distance formula, and that is the distance is equal to, let's see, velocity times t plus acceleration, well, let's see, 1/2 acceleration times t squared. And we've done this before because we already have a time to impact that we did when we initially were doing our stuff. So basically what we're doing for our time to impact is we're just assuming if we weren't thrusting, if we were just relying on gravity, when would we splatter onto the surface of the planet. So I'm going to go ahead and paste that in because this is just a quadratic equation. We can go ahead and solve this for t. So the distance is just the altitude that we currently are of. Actually, yeah, we can go ahead and set those up. We'll go ahead and say local d is out radar. So that's just the distance that we are off of the surface. We'll say local v is, and that's just our initial velocity, which is just going to be, let's see, what is it? Negative ship vertical speed. And let's see, acceleration is that same thing that we've got here, acceleration due to gravity. Let's go ahead and just paste that down here. Acceleration is that. Body mu, ship altitude, yep. And now we just need to solve for t. I'm just going to grab that real quick and paste it in. And there we go, return square root of blah, 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 blah. This is just the quadratic equation, but simplified, including this, half and at, and plugging in those values. So now this will go ahead and solve for t. We're basically just figuring out what is the amount of time at which our distance will equal the distance that we are currently looking for. Now, there's one last thing that we have to do, and I forgot about this earlier, but when we're actually doing our perform suicide burn, we need to lock our steering, because if we are just pointed in some random direction, then the throttle is not going to be particularly helpful. Now, we could lock our steering to, steering to surface retrograde, which is going to be the opposite of our retrograde vector relative to the surface. But if we happen to start moving upward, well, then we're going to start pointing ourselves downward. So I'm going to instead lock our steering to safe retrograde, which is another function that now we have to write. Go ahead and write a function safe retrograde. And we're going to say if ship vertical speed is less than 0, then return, yes, if we're falling, then great, return surface retrograde. I don't think we even need that. SRF retrograde. Else, well, actually, we don't even need an else. We'll just return, because if this was true, then we won't evaluate this. Else return heading 90-90. So if we are falling, then great. We should be pointing to retrograde. If we're not, then we should just go ahead and point straight up, right? And now with all of this done, we have, a rather long file, but we have all of these functions that we can look at independently and try and figure out exactly what it is that's going on without having to know the context, which is very, very helpful in trying to debug stuff. And I think now we've written all of the functions that we need to run. Let's jump over to the Launchpad and we'll grab one of our old craft and see how it does with this. So after a few minor typo fixes, we are out here on the Launchpad. We can see there it is. It is taken off at full throttle. We're using our old suicide burn test craft that we used many, many episodes ago. And we can see it's drifting off there. Now it's going to wait until it starts to descend, at which point, and now it's already deciding that it will crash if it doesn't do anything. You can see it's oscillating back and forth, so there's probably a bit of tweaking that we could do. But thankfully, we didn't end up hitting the VAB. But we have now this script, and we can go through and make tiny modifications. And you see we even forgot to put on to extend the landing legs. But we'll go ahead and update this and work on the next parts of our mission in the next episode. So I will see you then. Cheers.